and I want to know how many sections O of m has on Pn, and you compute, and you get n plus m choose m, and you sort of notice that that's the same as n plus m choose n, and you sort of, oh, the dimension. And you say, well, that's interesting, that's a dimension of h naught on Pm of OPM of n, right? And so I guess in fact, these spaces are naturally dual to each other. I guess I have to say, naturally is an overused word, but I'll do it. Dual to each other. Dual vector spaces. Actually, they're even naturally isomorphic vector spaces, but that's because we're working over SL2, and I prefer not to worry about that. But they're nice. They're nice. These are, of course, I guess any two vector spaces of the same dimension are dual. That's why I had to put some kind of a word in there, right? But yeah, I want to say naturally. So how does that work? So it's a motivating example, right? So how do I want to think of PM? I want to think of PM as, maybe I'll think of it as the Hilbert, or actually probably better to think of it as the symmetric nth power of P1, which is equal to the, you think of it as the Hilbert scheme of m points on P1. And I have Pn, which is sim n of P1, similarly. And I want to realize duality between these two line bundles. So I guess if I'm gonna, between these two vector spaces, so I'm going to do this by means of a divisor, which I'll just sort of optimistically call theta, inside of Pm cross Pn. And I'll think of this as, so if I'm thinking of these as parameterizing divisors on P1, I could just think of this as the set of pairs of divisors that intersect. That'll give me a divisor. In fact, I mean, easy exercise. Would be to show that theta is, get this right, it's a divisor of class n, it's a bi-degree nm line bundle, Pn plus Pn. In fact, let me torture the example a little bit more. I've got Pm here, I've got Pn here. If I pick, let's say, a general Z, by general I just mean it's going to look like the sum of distinct points. Then so I have this theta, which is this divisor living in the product. I can think of the theta of Z as a divisor inside of Pm. So theta intersect Pm cross Z. And that just looks like an intersection of, that just looks like a union of hyperplanes. So I have one hyperplane for each point, which is the subschemes of P1 that contain a point. Great. And then theta sort of gives me the duality, because I have H naught of, I have this theta, which is sort of represents is sort of the class of a section inside of oops, did I do it right? O of nm. But O of nm is H naught of O of n, OPM of n, tensor H naught of OPM of m, like some sort of seesaw principle. And then, so then I have this line inside of the tensor product, and that's giving me the map. which is in that sense natural isomorphism between them. You can even torture the example a little bit more, which I want to do because this is sort of this idea that got generalized, very nicely, beautifully by Marianne and O'Craft, which is I could choose. Let's see. So here's how I want to think about it. I want to think of an element here as y, but maybe I'll think of it as the structure sheaf of a y, of a subscheme y inside of, and I'll think of an element here as a structure sheaf of z in here. And where was I going with this? So I'm going to choose a scheme. I'm going to choose a subscheme W, which I'll just say it right this way. The class of W is the class of Y plus the class of Z, which is just a fancy way of saying that W has, the length of W is M plus N. And then I'll consider this is very fancy, but I'm going to consider the quotients, the quote scheme of length N quotients of W. Well, you know what that is. That's just going to be the set of Z inside W, such that the length of Z is N. I'm going to make W very general. Well, then this does even better. This actually picks out dual bases, because for every quotient, there's a kernel. And I'm assuming, yeah, W support is reduced subscheme. And so actually, there are, of course, we know how big this is, right? N things inside of M plus, this is subschemes of length N inside M plus N, so this is just our favorite number. Right? And so for every choice, so what is this doing? This is giving us a set of ZIs and then a set of WIs. Why? That actually, if you work it out, they form a dual basis. So this YI pairs with this ZI, the sections pair non-trivially and trivially with all the others. So this choice of this W, sort of general W, actually gives us more information than just knowing that these vector spaces are dual. It actually tells us that gives us a dual basis by choosing the quotients. So another example from Lepotier. No. I mean, I'm sure this was noticed by others before Lepotier, but I'll just put his name on there for the sake of a name. So I'm going to let S be a surface. Maybe over the complex numbers. Okay. And I want to consider. I'm going to let L be let's say a very ample line bundle on S. Let me consider two maps. I'm going to take a rational map from the Hilbert scheme of endpoints on the surface. I can get a rational map from this. Let me just finish my thought. I have two integers, two non-negative integers that add to the Euler characteristic of L. Maybe I will even want L to be sufficiently ample, maybe no higher homology. Let's do that. So then I get two rational maps from the Hilbert scheme of points on S to two Grassmannians, right? If I have n points on S, I can think of that as imposing n conditions on the sections of L. So I have a map to the Grassmannian H naught of SL of quotients of size n. Right? If the n points are general, then you take the this is the map from H naught of SL to H naught of this subscheme. Right? And I have another one for the Grassmannian of CM. And the point is that again, I'm going to have a the point is that again, I have some kind of a pairing. I can define some kind of theta divisor inside of Hilb n of S across Hilb n of S. So the theta divisor would be something like the well, we could take it to be the set of v comma y such that the H naught on the curve of L tends to the ideal sheaf of Z, tends to the ideal sheaf of Y. Maybe I want to be careful with that. Is not zero. The point is that if the points are in general position, you expect them to impose exactly the right number of conditions on the Euler characteristic to be zero, to have no sections vanishing on these points. This would be, for example, a total of 6 points on and you're looking at columns, right? And then when they move, and then there's a codimension 1 condition for these points to not impose independent conditions, and that'll give you a divisor inside of here. You can sort of see that this divisor is the pullback of the divisor from the Grassmannian of quotients. An actual divisor from here. And with a little bit more work, you can see that the theta z is, well, I mean, this theta looks like, theta looks like is the pullback of O1 comma 1. And now the theta is giving me a line inside of, well, wedge m of H naught of m, which is the global sections of O1 here, and wedge n of H naught of L, and m plus n is the dimension, so we well know that these things are dual, and the duality is, they're dual via this map, right? And the duality is sort of realized by the theta divisor.
So the duality, you want to construct some,
so my duality is between,
you don't want it to interpret the dual vector space as some global sections of something on the Hilbert scheme?
I do, so thank you. I was trying to put that under the rug, but yeah, I've got this n of S O of 1, which I claim that this is actually wedge n H naught of L, or n. And the other. So these actually fill they absorb all the sections of O1. Now what's interesting about this example, or interesting, maybe it's interesting because I'm trying to foreshadow a little bit, is that this theta bundle does not note theta is not in general ample, right? On Hilb m cross Hilb n. I mean, this is just a rational map. I mean, this is not in general an ample line level or an ample divisor. Okay, so let me shift gears for a few minutes, and then I'll come back to this. Come back to these two examples. Let's see what they have in common. So what I want to do is I want to talk about two constructions. I want to talk about determinant line bundles on moduli of moduli spaces of sheaves on the surface with a fixed E. So E is inside of H naught of S plus, it's a Chern class. It's inside wherever it is. So I want to talk about determinant line bundles on moduli, and I also want to talk about stability conditions on moduli. So let me first start with determinant line bundles. So here's the idea. So I guess I'll call this space extended Narron-Severé group of the surface. And maybe I'll even put it over Q. This is supposed to be the cohomology that receives the Chern classes. And I want to consider the vector space E-perp, which is going to be the perpendicular with respect to the Mutai form. So this is going to be the set of F inside of this extended Narron-Severé, such that I'll write this way, Slopples, the chi of Fe is equal to 0. So what that means is, i.e., chi of Fe is 0 if F and E were vector bundles representing will F and E. But it's a Riemann-Roch condition. It says that if, right, this says that if I pair F and the Todd class of S with E, maybe F dual, I get 0.
So this is a Euler characteristic of the, it's R home?
Yeah, it's the Euler characteristic of R home. So it's the dimension of home minus dimension of x1 plus dimension of x2. So I want to consider the perp with respect to this pairing. This works out better than just taking the ordinary Poincare pairing. And actually I want to think about two maps. So I want to think about a map from here to something that I guess we could loosely call the Narron-Severé group of moduli. Maybe I'll say simple moduli of class E on the surface. So just imagine a stack of simple sheaves on the surface. So yeah, so maybe I'll say, in a minute I'll say a tiny word about this. But so basically you should think of this, so an element in F perp is supposed to give me a line bundle somehow on the moduli space. And the way this works is well, I'll imagine I could represent little f by a vector bundle, and then on my moduli stack, if you like, we can work on the stack at this level. I'll have a universal family, and then I'll take my this LF will just be what I would get by considering maybe the R hom from pi upper star of F, this projection from here to this E, and maybe then I push forward down the moduli. Maybe I'll take a R, and I'll take the first Chern class of that. And for good measure, maybe I'll put a minus sign in front. Okay. The sign actually, yeah, ends up being minus. So that's my LF. So here's a little remark. Well, a couple of remarks. Why take something in ePerp? That's the first remark. And the answer is, well, this works fine for any E if I'm working on a stack of simple bundles. But it's the usual problem between, let's say, the Jacobian as a stack and the Jacobian as a scheme, as a coarse modular space. If I want something that lives on the coarse modular space, I need it to descend. And for the descent, I need this thing to be independent of tensoring this by a pullback of a line bundle from moduli. And this perp is exactly the right condition for it to descend. Sort of explains why, for example, you have a natural line bundle on G minus 1 of a curve, but not on. Okay. So the other remark is that to sort of make things look like what I had written before, if this set of E such that x1 of fe, so this was fixed, right, is not 0, you expect this to be, if this is a divisor, which is sort of what you expect, then the class of that divisor exactly computes this L. Okay, the divisor is a nice property. It's a reasonable divisor, then it should compute this L. So, yeah, so that's something I would call like my theta F. Okay, fair enough? So I've got a vector space here, a Q vector space, that's producing line bundles on modular space. And so this is a linear map. And so I can do things like ask myself which of these, so here's a little game to play. Suppose a good model for M, S, E exists. So for example, I mean, the game with surface moduli is it tends to be that for second churn, as you move the second churn character down, second churn class up sufficiently far, you tend to get good models of your moduli. And then for smaller values, the moduli can be kind of pathological. So let's assume we're not in a pathological sense. So then I have the I can sort of look at this from the minimal model point of view. I can say, well, I've got these line bundles on this moduli space, and I can ask things like, you know, especially if I need Z, and I can ask things like, you know, what's the Amplicona moduli inside this ePerp? Ask questions like that. Because ePerp is a machine for generating line bundles. So I can ask which of those line bundles are ample. I can ask which of them are effective. And we did ask these questions. You may have even heard talks on this, so
You have a board under this.
I know, I just...
Not this one.
It's on the right. The front,
Yeah,
the front one works. The back one doesn't.
I know that. I've seen it 4 times. Great. So we did an example like this. So for example, I can take S to be P2. And then ePerp, I can think of it as an element. I can think of it as an element that looks like a rank and then a C1 and then whatever it takes to be perpendicular to E. And I can map this now on my rank C1 line. Maybe I'll take E to be just to make things very precise, I'll make this to be the churn class of an ideal sheaf on the thing. And my moduli would be Hilbert scheme of ideal sheaves on S. And now I have this C1 and this R, and I can ask, I can start drawing pictures like this. So when R is 0, this ray here corresponds to the map from Hild N, the Hilbert homomorphism, to sim N. And then there's an ample cone for the, and in general, these C1R, under this determinant construction, go to this symmetrized C1 minus R over 2 times the exceptional divisor on the Hilbert scheme. So that's what happens. So I'll have an ample cone in here, and then I'll have some effective cone, I'll have some final ray, and yeah, this has been, so both of these, this we knew. So there's work that I did with Izet Alcara, and I don't know why I put Izet first. Okay, and then I don't know why I put myself there. Jack goes last because he was a grad student when we did it. Okay, so but we investigated this thing for many values of n, and sort of found this first ray. But then in subsequent work.
Can you say again what's the significance of the first ray?
The first ray is where the line bundle on the Hilbert scheme becomes Neff and not ample anymore. Stops being ample. Which you can well imagine, you can figure out where that happens. And what does it do? It contracts some curves in the Hilbert scheme. And the curves in the Hilbert scheme are exactly the curves of points, all of which lie on a line. So that's easy to compute. That was known. But getting these further arrays is a little bit of a challenge. Yeah. So what Jack and
so all these cones are ample cones of birational models.
These ample cones of birational models, and I have to tell you, if I don't use up all my time before, well, I only have good. I'm on time here. I have to tell you what those models are. So the point of our work, actually, of our paper, is actually to tell you that these models are moduli spaces of stable complexes. And that will be the second map that I promised you. But I just wanted to give you a taste of how this stuff works. So if I took, yeah, so this is the picture that you get for ideal sheaves. If I took E to be, let's say, 2, and then maybe C1, and then some n, minus n, then you get a similar looking picture, starting with the moduli. So this would be a moduli space of rank 2 bundles on P2. And you'll get a similar picture, because this ray will correspond to the map to the Uhlenbeck compactification, which contracts the sheaves that are torsion-free but not locally free, which form a divisor. So what these guys did is identify these 2 rays. The first ray where the line bundle fails to be effective, and then the last ray where it fails to be, where it fails to be ample, then the last ray where it fails to be effective. And they did it in higher rank, but in higher rank the picture is kind of amusing. I don't know if this phenomenon was sort of known, but the map to Uhlenbeck, if you go to rank 3 or above, does not contract a divisor, it contracts higher codimension. And so this is actually passing over Uhlenbeck corresponds to some kind of a flip. And on this side you have the ample cone for the moduli of E, and on the other side you have the ample cone for the moduli of the sort of the Serre dual. All right, this way. For the Serre dual. So you've got sort of these, they sort of fit together in this picture. If I was being hardcore Bridgeland stability guy, I would sort of say that's going to be the moduli for E shifted by 1, but I'll talk about that later. A minus E. And so again, they figured out these rays. And I think it's safe to say that at least ideas from derived categories were motivational if it happens, it may also happen to be true that a posteriori, after you get the answer, you sort of figure out how you might have gotten it without the derived category. It's a little bit of a bummer, but yes.
I assume it's known that there are other rays in between.
Lots of other rays in between. There are rays, oh, I should say this. There are rays in between that correspond to points you can imagine. There's sort of more points on curves of low degree than you would expect. But there are also rays in between that correspond to vector bundles on P2 whose sections vanish at points that are not general. So there are all kinds of interesting rays, and there are multiple rays. There are rays where several interesting things happen at once. So the birational geometry of what's happening to the Hilbert scheme, what kind of flips there are, is very complicated. Although the model that you get at this point is at the very last ray, the model is a Kronecker moduli space, which the people that were here the first half hour know what it is. You have to ask the graduate students what that is. So what about the other map? So the other map is the map that's supposed to tell me what these modular spaces are. So here, this is a little fancier. So this is Bridgeland's manifold of stability conditions on S. And so a stability condition consists of two things. One is we need a slope function, which is analogous to the ordinary slope for curves. And then I need a t-structure, which doesn't really, on the derived category of coherent sheaves on the surface, that sort of supports the slope function. So I just have to tell you what these things are. So if I'm given E, and this in some sense this is my work that's sort of interpreting, sort of understanding this map in this sense. So yeah, if you want more details of what I'm saying, look at the paper I put for Rob's birthday conference. So the idea is if I'm given an F in here, my slope function is going to be a ratio of things, and the top is going to be designed exactly so that the slope of something of class E is 0. So I'll take this chi of FE. I've got an F in here. So this is, and then the bottom is going to be some kind of funny rank. And actually, I still haven't, okay. So this we'll say is F dual just corresponds to the class of a dual bundle. So if I have an F, then F dual just switches the sign on the first Chern class. F dual. If F is F0, F2, F4, F dual is F0 minus F2. That's all. So this is just a Poincare pairing by Riemann-Roch of this guy together with E. Oh, and I should say, I'm sorry, let me be careful. I want to talk about mu of an object. So I'll call my object A. So I'm going to take chi of F together with the Chern character of A, and I have to divide by a rank. So this is supposed to be analogous to the degree. What is degree? Degree is just some linear map from the Chern character to the real numbers, let's say. Right? So this is, so that's pairing with the cohomology class. So I'm just going to pair with this cohomology class F, which is considerably more complicated than a hyperplane class, but it's still a cohomology class. So that will be my degree, and my rank will be, I'll toss in an H, where H is going to be an ample class. I really wish I didn't have to do this on the surface, but there is a choice of an H in choosing what the rank function is. That's my slope function. You should think degree over rank. And then the T structure on this is exactly designed, okay. I'm not going to tell you what a T structure is. I'm not going to, what I will just tell you is what the outcome of this T structure is. So T structures determine abelian categories. The standard T structure determines the category of coherent sheaves. The particular T structures that we'll use here will give me, the T structure will determine the heart of the T structure, which is going to be a category of two-term complexes. I don't think there's any harm inside the, I mean, it's things quasi-isomorphic to two-term complexes inside the derived category. I think there's no harm in thinking of it as a pair of vector bundles with a D map.
So minus 1 D0.
Complex, let's pretend a vector bundles so that I will have the co-kernel of D, which is a sheaf. And then I have the kernel of D. To do this right in the derived category, you shift by 1. This is another sheaf. So it's complexes that produce these pairs of sheaves, and sort of morally, this should be made up of sheaves of large slope, Mumford slope, and these should be made up of sheaves of small Mumford slope. Really what's going on is this is designed so that this funny rank function, if I apply it to these sheaves, so that, okay, I'm going to write S, I'm going to write E prime in here, a subsheaf of this guy, and I'm going to write an E double prime as a quotient sheaf of this guy. So this is designed so that the rank of E prime is negative, S equals 0, for all E prime inside the kernel. And the rank, this funny rank function that I find down there, of E double prime is greater than 0 for all quotients of the co-kernel. And it's a result that relies on harder C-line filtrations for Mumford slopes that this defines an abelian category. So you should think of these two-term complexes as fitting into an abelian category. So I have a map between two of these guys with these properties. I can take kernels and co-kernels and sum them, etc. Okay. This is the category, so I'll call this category A sub F. If it depends on the F, that's the point. So the category depends on the F, the slope function depends on the F. And this map to this space of stability conditions is exactly this map. So I take an F, I go to this slope function on this category of two-term complexes. And I can ask about stable things. In fact, I can look inside of the space of stability conditions, and I can ask, what do the objects that are stable? I can tell you what stable is. An object is stable if all sub-objects have smaller slope. So I can ask, what are all the stable objects in here? Maybe if I'm really ambitious, I'll say, what are the moduli of stable objects of class E? So I'll call this something like ME, depends on F. And there's this hidden dependence once and for all on H, which you don't like. Notice that there's sort of a curiosity that in fact, if I look at stable objects of class E, the rank is actually irrelevant. Because the numerator, if I have class E, is 0. So the condition for being stable is just that any sub-object should have smaller slope, but that just means it has negative Euler characteristic. So the result, the Stability manifold gets a wall and chamber structure from this condition. So there are chambers in which the moduli spaces don't change, so stay constant. Then there are walls where semi-stable objects show up. They need to be, objects become semi-stable and then unstable when it crosses the wall, and I get some other moduli space on the other side. And the really great result of Bayer and Cree says that these walls and chambers match up. So I get a wall and chamber structure on here from looking at the wall and chambers for the minimal model program, sort of on the line bundles on a model of the moduli space. And I get a wall and chamber structure here on where the moduli of these stable complexes switch character. And the result is basically that these line bundles are, these line bundles that you construct here are actually ample on the appropriate, within a wall. And then they exactly contract the families of objects that become semi-stable when you hit a wall. Yeah. Yes?
On the right, you have just a cone which you decompose.
Yeah. Oh, okay.
Left, you
Right.
have
So this is not the whole stability manifold. This is a slice of the stability manifold, and this slice is. If I have a contribution to this, it's just that it's that these under these coordinates that you sort of impose on this, the walls are actually affine linear. They're actually or linear actually. You get a cone. These walls become a cone structure on the E-perp. They become the walls of the cones. Does that make sense? So I've sort of got this blob here with all these funny walls, but then I've got this E-perp sitting inside of here, and here the structure is that of the wall and chamber structure is that of the walls and chambers of a cone, in a cone decomposition.
So are the moduli spaces empty beyond a certain?
Yeah. So I've hidden some things, some difficulties. One difficulty of this map is it's only defined on a certain part of E-perp. Basically, there's a part of E-perp where some analog of the Bogomolov inequality has to hold these things. So it's only defined on part of it, and which is natural because.
On the right, you only have part.
And then the other thing is that these moduli, I mean, the wall and chamber structure might just collapse, just as it does on the other side. It might just collapse all your moduli, and then you don't have anything interesting going on the other side.
So the projectivity of the moduli space of stable objects, this is due to what?
Okay, so maybe I should say a few results. So the result of biometry says that these line bundles are positive on the moduli spaces of stable things in an appropriate range where everything is defined.
Ampleness. Positive means ampleness?
Yeah, that's the catch. So they know that these line bundles are positive when paired against all curves. I would say that it's ample if we could use Kleinman's criterion. Cases where we know that it's actually ample are when S is a Delpetzel surface, K3 surface, Abelian surface, Enriquez surface, maybe a few other examples, not so many, but it's not known in general. So for example, we don't know that a priori you might reach a wall in here, and then on the other side you get an algebraic space with a positive line bundle on it that's not projective. So that is a sort of an open problem in general.
Positive means net and actually positive on effective.
Positive on effective curves. Okay, so let me get back to strange duality. Sorry. So probably the right way to understand this strange duality now is on a surface is, so I'm going to have a pair. I'm going to be given a pair of, let's say, vector bundles, so chi of EF is 0. And so of course that implies that E is in F perp and F is in E perp, right? So they sort of give determinantal line bundles on each other's moduli. So in fact, I could do this. I have the moduli of E, and then I have the moduli of F, and then maybe I'll cross it with the surface, and then I'll have an R hom from, I'm just going to be sloppy and say from F to E, but you know what I mean. I have the F is defined here, I pull it back. The E is defined here, I pull it back. I take the R hom, and then I push forward to the product of the moduli, take C1, take minus. That'll be the line bundle I want to call my O of theta. This is on M cross M. Now the nice thing is that by the theorem by Byron-McCready, if I'm careful, and again I have to make sure the various conditions are satisfied, but if I'm careful, I can use each of these to define the right moduli space for the other one that will, so that theta is actually positive. And if we take even ample, if S is del Pezzo, for example. Okay, 3 or B. So the basic sort of conjecture of the Potier was that I could use, so if, it says that if theta is actually a divisor, oh, so what data would I pick? It would be the pair so that x1 of fe is non-zero, which I'm expecting to jump up in codimension 1 on a divisor. So if this is actually a divisor and not a pseudo-divisor, not actually vanishing everywhere, then this C, which is sort of the section that defines theta, this determines the perfect pairing.
So C is 1 sub theta.
Yeah, multiples of theta, if you like. Is that okay? I could. You know, I mean, we have a section that defines the zero section of the section. So this defines a perfect pairing between the two. I guess I should say a word about why I stick to del Pezzos. Well, in the case of del Pezzos, you can use the seesaw principle, basically. So that once these are log fauna or rationally connected or something, so that I know that any line bundle on the product decomposes as a box tensor product. If I was working on an interviewing surface or a K3 surface, I have to talk to Marini Oprea and be much more careful about how to work, because these stated bundles are not, in general, essentially never box tensor. Yeah, they vary. One of them varies on the other edge.
H not of what?
Yeah, thank you. This is the LF, and this is the LE. So the line bundle on one determined by the other. Okay, so with my students in the last 2 minutes, I'll say what I've been doing lately. We've been looking at the following case. We've been looking at an example it's supposed to be similar to the original. You're supposed to think of sort of analogous to the original Hermite reciprocity example. So I want to look at an example where E is an ideal sheaf and F is some vector bundle. I don't care, but it's F is in E perp. Okay? And what I want to do is I want to try to find, the idea is to find a V, a very general V, on my surface of class V equals this ideal sheaf plus F, and then I want to consider the quote scheme. I want to consider the quotients of V of class F. So the idea is that then I'll have these FIs. I probably meant class E, sorry. So then I have these EIs, which are these. If I'm lucky, this chi EF being 0 condition, right? Or chi FE being 0. That sort of should be satisfied by saying the HOM is 0, the x1 is 0, the x2 is 0. If the HOM and x1 and x2 are 0, then this quote scheme is actually finite because the Zariski tangent space is the HOM. And in fact, this will be, if I find these things, then just as in the Hermite reciprocity case, I will find the expectation is that we will find dual bases for the two sides. So what do you need to do? Well, you need to do two things. One is you need to do a computation to check that the size of the quote scheme you expect to be the same as the dimension of this space of sections. Because again, in Hermite reciprocity, that was number of subschemes matching with this computation. And then the second question, which is much harder, is to find a V that is sufficiently general so that the quote scheme is actually finite. And so then it would realize dual bases on both sides. Hidden in there is why I have to do delta surfaces. Such a vector bundle can't exist. So we did some computations. So let me just,
Is it the
oh, I have still 5 minutes. Yeah.
dependence on the bases are on V? Is what we can.
Yeah, it's very cool. So the V will be fixed, right? The idea is to find a fixed V. So like in my other example, I was finding just a W. I just chose like n plus m points.
Mm-hmm.
So I have a fixed V, and I want to look at F quotients. And the idea is if I finally many, and I'll get these FIs on one side and the ideal sheaves of ZIs on the other side, and these will give me dual bases for my space of sections of determinant bundles on both sides. And so the first question that should come up is it true that that the size of this quote scheme, I'll just write this one, is actually the same as the dimension of the sections of the appropriate bundle, and the bundle is, I'll just tell you, we're on a Hilbert scheme of n points on S, and my bundle looks like O of, it's going to be this C1 of F, this n thing, minus the rank of F over 2 times this exception, O exception for the Hilbert scheme. That turns out to be the computation. Okay, well, this line bundle is an apple. That doesn't turn out to be a problem. It still has no hypercohomology. We could move to the appropriate model of the Hilbert scheme by looking at an appropriate moduli of complexes. It doesn't really matter, but this is the same as the Euler characteristic. And this thing has been computed by Gertsch, Ellingsrud, and somebody else. His name escapes me at the moment. Strum? I don't think it's Strum. Anyway, somewhere around 1999, by some cobordism argument or something, they computed these dimensions of these spaces, and so we were interested in these spaces. So together with a couple of graduate students, we and myself, we set about computing these things. So why is this computable? Well, here's the idea. Suppose I'm looking for ideal sheaf quotients of a vector bundle. Right? Well, that's this vector bundle embeds in the space of sections of its duals. So this will embed in some giant ON. Now have a W, which is the quotient. And so the quotients of V will correspond to these scheme theoretic quotients of W, which is is actually finite, then actually the quote will correspond to a self-intersection locus. So the n self-intersection locus of this map from P of W to projective space. I'm looking for, schemes. Yeah, looking for these. Anyway, that's what happens. And so this turns out to be not so easy, I think, to calculate. So we've calculated this with the help of, it's not so bad for double point loci. So the nth intersection, when all the numerology works out, this nth intersection locus is expected to be distinct points. So I'm trying to count these points. And so we did it for double points, and then we found a whole slew of literature, some by my co-author, Senesh, and other Romanians.
Senesh is not Romanian.
Hungarians. Oh my God. That did not leave this room, okay. Okay.
He's on video.
That's on video. I have the So there's a series of papers that have titles like quadruple intersection formula and quintuple intersection formulas, where we have to, and then they have a conjectural sort of general picture for what's happening, and and so the upshot is that every time we've computed these things, they've matched. Which again means, what does this mean? This means that now, of course, we're working on trying to find general enough bundles, but it means that if you find a general enough bundle of this class, then this quote scheme will give us a basis of the space of sections of an appropriate line bundle on the Hilbert scheme. So what's missing, of course, is this side. We don't know how to compute the dimension of it. So what could happen is that this space on the other side could have conceivably larger dimension than we're expecting, and we're only picking out a finite collection of independent sections. We don't believe that's true, but that's where we are. So maybe